All right, everyone, welcome back. Quick and easy chapter today about security built into the switches and the routers that you already have. So before investing into more complicated and more complex security devices, let's properly leverage what's already in our network. Now, as we talked in the previous video, a lot of the traditional protocols that we still use nowadays, starting with IP or IPv4 and the address resolution protocols, are inherently insecure. That is, there's no security built into them because they just weren't designed with security in mind back then when, well, things were so young and everybody was so eager to invent something new that simply worked and didn't have to think so much about security. Now, nowadays, we do have to think about security, and fortunately, a lot of the traditional devices that we already have in the network, like switches and routers and access points and wireless LAN controllers, they do have security functionality that can be enabled. Now, it's built into them, it's not enabled by default, but it's there, and you should be aware of that before going on and buying expensive hardware, security dedicated hardware. And starting with switches, even layer 2 switches can enable security functions that are extremely effective, even though they are extremely simple, actually. And at layer 2, fortunately, there's not much that can happen from a security perspective, but most attacks are going to focus on eavesdropping on network traffic. That is, intercepting that traffic and being able to read it even though it wasn't destined for the attackers. It doesn't necessarily require the attacker to be on the traffic path. We're trying to focus on a couple of methods that we can use to trick the networking devices, especially the layer 2 switches, and the way the ARP protocol works, that we are the legitimate destination for that traffic. All right, so I'm going to see some interesting examples right now. Now, the most common method of intercepting traffic, and also the most generic one, is called the man-in-the-middle attack or the on-path attack. This requires the attacker to actually position themselves within the traffic flow between the source and the destination. Now, of course, a couple of methods in place can ensure that this doesn't happen, such as not being able for the attacker to position itself between the source and the destination, or by using encryption. So we are assuming that an attacker could intercept the traffic, but we can be pretty sure that they would not be able to decrypt it. Now, not everything can be implemented at layer 2. Again, we're focusing just on layer 2. So man in the middle could be about an attacker placing themselves inside of the traffic path. It could also be about spoofing, for example, DNS requests, and then replying to a simple client that is trying to access a website with a fake website. Thus, the attacker being able to intercept perhaps the login credentials to that website. That's also a man-in-the-middle attack. It's not just about eavesdropping on traffic. If you manage to intercept that traffic, you can probably modify it or alter it in some way, thus affecting the integrity of the traffic. And the most common method for performing a man-in-the-middle attack on layer 2, so within a single subnet, is by performing MAC address spoofing. That is basically about announcing a fake MAC address instead of the real one. Now, it's not just a matter of, generating a random number for that MAC address, but of course, ideally, an attacker should announce themselves with the MAC address of somebody else on the same network segment, thus attempting to overwrite the entries in the CAM tables of local switches, and after correctly answering a couple of ARP requests with spoofed ARP replies, all the traffic that is legitimately destined for another destination in the network is going to reach you as an attacker instead. Now, MAC address spoofing can easily be done in most operating systems, including in virtualized environments, so it's not really a method that requires a lot of expertise. You simply overwrite the MAC address that the host is going to announce. Sometimes this feature is going to be called MAC cloning, especially when you're actually stealing somebody else's MAC address and you start using it. And actually, the biggest and most problematic protocol that we find in layer 2 is the protocol that allows us to communicate in layer 2. That is ARP, Address Resolution Protocol. If you remember from the previous video, we said that's used whenever a host attempts to communicate with another host. They know their IP address, but they don't know their MAC address in order to build those frames. All right, so they send an ARP request. It's a broadcast. Everybody receives it, and the legitimate host that actually owns that IP address replies with a unicast message saying, "This is me. I do have this IP address, and this is my MAC address. So you can start sending traffic to me." Now, there's no security here. There's no authentication. There's no encryption. Everybody can see those ARP requests. Everybody can answer those ARP requests with fake ARP replies, which means that if somebody else wants to impersonate us, it's on the same network as us, nobody's stopping them from answering instead of us, right? With a fake ARP reply, basically becoming the destination for any traffic that was supposed to reach us, which is pretty bad. But actually, the bad news don't end here. Unfortunately, the ARP protocol was designed in such a way so that a host can learn from an ARP reply even without having sent an ARP request from the very beginning. Because ARP is completely stateless. It doesn't hold any state information. It cannot actually connect requests with replies. So whenever a reply comes in, every host is basically going to say that, wow, this is useful information. I'm going to use this. Who cares if I did not request it? I've received an unsolicited ARP reply with useful information. I'm going to learn from this information and start using it, which means that it's awfully easy for an attacker's host on a subnet to basically tell everyone on that subnet fake information about specific destinations. Now, the most widely encountered scenario involving ARP spoofing and MAC spoofing is for an attacker to present themselves as the default gateway in the network, telling everyone, hey, the default gateway just changed. You know, this is the new MAC address of the default gateway. If you have anything to send to the default gateway, which is probably going to be traffic destined for the internet, send it to me because I'm the default gateway. And everybody's going to believe them, right? And there you go. You suddenly start receiving all the real traffic that is supposed to go to the internet. And that's a very legitimate and powerful man-in-the-middle attack. Now, of course, you should perhaps take care to reroute that traffic to the real internet gateway so that you can be able to actually look at the real conversation between your clients and any destinations on the internet, because you're probably trying to intercept some passwords in there. You're going to want to look at some chat messages and perhaps emails and such. So let them flow, right? Don't just break the connection right there. Make sure that the actual traffic can reach the intended destination, even though you're in the middle, right? You're the man in the middle. So basically, ARP spoofing or ARP poisoning is about injecting this fake information in somebody else's ARP table, right? Every operating system stores an ARP table. They remember who they communicated with in the past and all the replies that came in the past, so that they won't have to send a request and reply every single time they want to communicate with somebody on the network. And keep in mind that unsolicited ARP replies are a very dangerous behavior that is enabled by default in every network and is facilitated by the actual implementation of the ARP protocol. Now, a couple of the tools available that you can use to perform attacks such as these, or tools that attackers are going to be using, are called AirCap, DSNF, RSpoof, or even the Metasploit framework has plugins and modules built into it that can launch an ARP spoofing attack. Now, if you also have an older operating system because it's not supported anymore, you could be using the Kane software as well. If you're running on an older OS, that tool also had a built-in functionality for performing ARP spoofing. Again, for the exam, you don't really need to know how to use these tools. Just make sure you can recognize them out of the list if the exam asks you to. Now, we also have layer 2 attacks that are destined for the actual switches that ensure communication between the hosts. Now, as you remember from the previous video, switches do have a CAM table that they use to forward traffic to the right ports. And they learn the information that reaches those CAM tables simply by looking at the source of traffic. If they see a specific matters coming in from a specific port, they store this information just in case at some point in the future somebody's going to want to communicate with that destination, and they're going to know exactly where it is located. Now, when the CAM table is completely empty, it's for the switch to broadcast any message that it receives onto all the ports, because it doesn't know where the destination actually is, but it knows that if it forwards it to all the ports, eventually it's going to reach the intended destination. Now, there's also a behavior that happens whenever the switch memory is full. So when the switch cannot learn new information and the destination is not within that table, what does it do? Well, exactly the same thing. It starts flooding information, flooding traffic out all the ports, which means, and I'm sure you're already thinking about this, well, what if we start sending bogus traffic with fake randomly generated MAC addresses to the switch up to the point where the switch memory becomes completely full? Well, when the switch memory becomes completely full, any traffic that tries to reach that switch is not going to be able to find a valid destination because we just filled it with bogus information, right? And the switch is not going to be able to learn new information again because the memory is full. So what is the switch going to do? Well, it's basically going to transform any unicast communication in the network into broadcast communication, which means that if we are an attacker connected to the same network segment, we just have to listen up, and all the traffic within any host inside of that network is going to reach us as well. So it's a very, let's say, violent type of man-in-the-middle attack that can be performed, basically tricking the switch into sending all the traffic that it sees onto all the ports that it has, including the one that you're connected to, you as an attacker. So that's another type of MAC flooding attack. Loops at layer 2 basically represent specific types of topologies where the networking devices, the switches, the layer 2 switches, are connected in a cycle. All right. So loops from a physical perspective are good because if any connection within that loop breaks, let's say there's a fault, maybe an interface dies, maybe even an entire switch ceases to function, we still have an alternate path available to us and to all the other devices that can connect to the other switches so that they can still communicate with each other. So we have physical loops which are okay. Now, logical loops, that is loops in the actual traffic path, well, at layer 2, they're not so good. Because at layer 2, if we look at the generic Ethernet frame structure, unfortunately, there's no such thing as a time to live or any loop prevention mechanism. So if it just happens that due to a faulty design, our frames start cycling around indefinitely inside of our network, they're going to keep doing this forever unless we actually pull the plug on a network cable or on the actual power of a switch. So there's no loop prevention mechanism built into layer 2 frames, which means that we need to rely on protocols that ensure that these logical loops, when they happen, they don't break the network. And this is where STP comes in. That's a spanning tree protocol. Now, the spanning tree protocol, again, without going into too much detail, because this is not a networking training, it's a protocol that runs between layer 2 switches, and they constantly communicate information on the links between those switches, so that whenever a physical loop is detected, those switches take care of manually shutting down specific interfaces so that a logical loop doesn't happen. So basically what it does is that they transform a cyclic topology into a tree topology. If you remember from data structures and algorithms, perhaps back in your college days, a tree data structure doesn't have any loops, just like the branches of a tree, right? There's no loops in there. It's just branching and branching and branching, and that's it. But there's no way for a packet to cycle back to the same device. Now, the tiny packets that are communicated between the switches that are running STP are called BPDUs, which stands for Bridge Protocol Data Unit. It's just a small packet, including some identifiers that helps these switches decide which ports they're going to shut down temporarily just to avoid loops, which is going to be the root of the actual tree that is being built as per the STP algorithm, and so on. Now, again, STP is a very old protocol. BPDUs don't have any kind of security built into them. So potentially, an attacker connected to the network could present themselves, even though they only have a workstation or a laptop, they could present themselves as a switch, as a layer 2 switch. And they could fool the other switches in the same network into believing that the attacker's device is an actual switch that can switch traffic. Now, by using these fake crafted BPDU packets, they could potentially change the actual topology of the STP tree. And this would be another way to implement man in the middle. Present yourself as a switch, make sure that all the other switches reconfigure their topology so that all the traffic flows through you. All right. Now, in order to avoid this, we can simply mark specific ports on our switches, configure specific ports to reject any BPDUs. And that's implemented as something called BPDU guard. We're just rejecting BPDU packets because we know that BPDUs are only supposed to be sent by legitimate switches. if we know that all our access ports, the ports that connect to actual workstations, are not designed to connect to any other switches, we can simply block BPDU traffic onto all of these ports, thus avoiding situations where an attacker might present themselves as a fake switch. Finally, another very simple method of avoiding potential attack, especially denial of service attack in a layer 2 network, is by enabling something called a broadcast storm control, or just storm control sometimes. What this actually means is that, as you probably know, a broadcast is going to pass through a switch unimpeded. So a switch by default forwards broadcast messages onto all of the ports. Now, potentially an attacker could attack the STP infrastructure and create a loop inside of the network, intentionally create a loop inside of a network. Now, if a broadcast message were to circulate to reach that loop, is going to continue looping in that specific piece of infrastructure indefinitely. This is going to lead to very high CPU utilization on those switches, saturated links that cannot send legitimate traffic anymore, thus basically creating a denial of service attack into the network. So it's not just a matter of attacking layer 2 network for eavesdropping on traffic, but it's about attacking the network to make it stop functioning properly. Now, broadcast storm control is just a matter of monitoring the usage of all the ports for specific thresholds. Now, if we keep seeing the same frames looping around and around over the network, and we see huge traffic spikes onto specific ports, then we can simply shut down that port or just block that specific MAC address from ever communicating onto the switch again. Now, what about actually filtering traffic at layer 2? We know that at layer 3, we have routers and firewalls, and we can create access control lists that allow or deny specific types of traffic based on their IP addresses or subnets that they belong to. Well, what about layer 2? Well, at layer 2, we can only filter based on MAC addresses, of course, which means that, of course, certain layer 2 switches allow us to create something called a MAC access list, which is basically just a list of MAC addresses that are allowed to communicate through a given port. Now, this is also sometimes implemented in a global manner over the entire switch, and it's called MAC address filtering. It's just a matter of defining a list of allowed MAC addresses that are allowed to send traffic through that switch. Of course, we can even adopt a block list approach to this implementation, and instead define a list of MAC addresses that are not allowed to communicate over that network, which of course is not really practical, since MAC address spoofing is painfully simple to achieve, so you're not really gaining much security by trying to capture all the malicious MAC addresses onto a single list. A whitelist approach is much better. Apart from the actual MAC address filtering, which you can probably guess it's not going to be very convenient and it's going to require a lot of admin effort, we could instead implement something called port security. Now, Cisco calls it port security, some other vendors call it port security as well. Well, basically, it's just a way of automatically manage the allowed MAC addresses onto a switch. How can you automatically manage this? Well, unfortunately, there aren't many methods. So apart from manually configuring the MAC addresses, which we just said is not very convenient, we could do something a little smarter. That is, once we power the switch up, and once all the hosts connected to that switch start sending traffic, we tell the switch, hey, look at the first MAC address that you see on each and every port and store that MAC address in your memory. And also make sure that no other MAC address is going to be allowed on that port from now on. So the first type of traffic that the switch sees is considered to be legitimate traffic. Ideally, this is going to happen in a controlled environment, right when you actually install the switch. Hopefully the attacker is not already in the network by then. And then the rest of the traffic is going to be filtered based on that initial information. So everybody boots up, everybody comes into work Monday morning, they boot up their workstation, the switch remembers, aha, so these are my legitimate destinations. These are my legitimate workstations. I'm going to store them in a permanent memory. So we're not talking about the CAM table here. We're actually talking about a specific table that is designed to ensure this port security implementation. Now, of course, we could increase this limit. That is, we might be able to allow maybe 2 or 3 MAC addresses onto every port, which is a very common scenario if you have an IP phone and a desktop workstation and perhaps a laptop on your desk as well. So you're going to need, well, 2 or 3 MAC addresses in order to maintain connectivity, but nevertheless, this implementation eases a lot of the administrative burden of manually configuring whitelisted MAC addresses. Some people call this a sticky MAC address implementation. That is because the actual Cisco iOS command is MAC address sticky. So we call it sticky because, you know, the first one that we see kind of sticks right there on the port, and it becomes the only allowed MAC address. Now, as you can probably guess, we're doing this MAC address sticky port filtering business in order to avoid situations where an attacker is going to impersonate a legitimate user. So we're doing this against MAC address spoofing. Now, there's another problem here, which port security doesn't fix, and that is ARP spoofing. Remember, we said that the ARP protocol is designed so that even if a reply is received without any request being sent, that reply is still going to be processed by each and every host. So unfortunately, while port security doesn't help us with this, we do have a method of mitigating this type of ARP spoofing as well. And that relies on a feature called DHCP snooping. Now, DHCP, the Dynamic Host Configuration Protocol, is a protocol that you're probably using in your home network, in your office network. Whenever you're connecting to the network, you're receiving an IP address, a DNS suffix, a subnet mask, perhaps some additional information automatically from the network. So it's a way for you to automatically configure your network card the moment you connect to the network. All right. Now, this DHCP protocol, again, it's a type of request response. We send a request as a broadcast. There's a unicast coming back here as a response. And after you've received a valid IP address, you assign that IP address to your network card, you can start communicating over that network segment. And also with the default gateway, which is most likely an information being received automatically through DHCP as well. Now, this type of traffic can be very useful in identifying who is connected to which port. Unfortunately, by default, nobody's looking at this information. Nobody's looking at DHCP traffic, but we can configure our switch to inspect, to snoop on the DHCP traffic in the network. So the switch is going to just look at the DHCP traffic that flows through it. It's going to see the requests, it's going to see the replies, and silently is going to remember which hosts, which IP addresses, and which MAC addresses are located on which ports. So we're going to build a small database of everybody who is connected to the local switch. And then, if at some point an admin enables another feature called dynamic ARP inspection, the switch is going to start looking at ARP requests as well. Why does it do this? Well, in order to identify ARP spoofing. With ARP spoofing, eventually we're going to see an attacker that announces themselves with a different MAC address than the one it was initially detected on that port. And the switch knows about this because the switch knows the original MAC address due to the fact that it was snooping on the DHCP traffic from the very beginning. So it knows which hosts with which IP addresses and which MAC addresses are connected on which ports. So if somebody starts goofing around and starts announcing a wrong or different MAC address, the switch is going to catch it immediately and is going to deny that traffic. And this combination of DHCP snooping with DAI, dynamic ARP inspection, ensures that a ARP spoofing, man-in-the-middle attack, suddenly stops being possible within our network segment. And we don't need any additional devices for this. This is just functionality built into many, not all, of course, layer 2 switches nowadays. Going up in complexity as to the security methods that we can implement into a single network segment, we suddenly reach the functionality called Network Access Control, or NAC, or Network Access Protection, or PNAC, or PNAP. Any kind of combination of acronyms here actually refers to the same thing. And because there's a lot of confusion here, we actually have a standard behind it, which is called 802.1x, Network Access Control. Now, this is a type of protocol or security method that can be implemented at switch port level. Again, we're only talking about layer 2. And we can configure that switch port to make it mandatory for whoever connects to that switch port to present some sort of authentication information before being allowed to communicate further through that switch port. If we're talking about switch ports here, it doesn't mean it only applies to the wired environment. You can also apply this in wireless using access points, right? But for the sake of simplicity here, because we also have the screenshot here with the with the Ethernet ports in here, we're just going to focus on the wired equivalent. Now, there are a couple of protocols involved in this communication. Some of them are under the umbrella of EAP, Extensible Authentication Protocol, and the actual protocol that is allowed between the device that connects to the port and the switch before they're even authenticated is called EAP over LAN. That's a protocol that can carry authentication information that the device can present before they're being given access to the rest of the network. Now, that authentication information can be as simple as the username and the password. Could be as complex as having received a web portal where they could authenticate perhaps using a third-party device or a smart card or one-time password. It could even be based on a certificate that is installed on that device itself. All right. We can even perform separate device authentication and separate authentication for the user of that device. So there's a lot of complexity built into this. Fortunately, you don't really need to know all this for the exam, but the important thing to know here is that any switches that support this type of authentication are going to have to rely on an external database as well. In many situations, that external database is called a AAA server. That is an authentication, authorization, and accounting server, which could be a Radius server, which could be your LDAP server, your Active Directory server, perhaps in your network. It's going to be a centralized database of whoever should have access to the network. So the switches receive those authentication requests, forward those authentication requests to the AAA server. They receive a yay or a nay, a response from that server, and then in turn dynamically reconfigure the port that you're attempting to connect to either block all access or allow access according to your credentials and your identity. Now, optionally, we can also augment this authentication mechanism with something even more complex that is called a posture assessment. So we're not just looking at, let me see if you have valid credentials, if you know the password, whenever you're requesting access to the network, but instead, I'm going to try looking at your actual device. Let's see, are you running Windows? Are you running Apple iOS? Are you running Linux, Mac OS? Do you have the latest updates? What versions are you running? Is it a jailbroken iPhone or not? Do you have an antivirus installed on your device? Is the antivirus has been updated during the last 2 weeks? Right? So there's a lot more complexity that we can add here to the actual authentication process to make sure that we're only allowing legitimate devices and safe devices to connect to our network. Now, as you can probably guess, this type of implementation requires quite a bit of admin effort, but once it's being put into place, it's completely automated. It doesn't require any manual configuration at the port level. Any device that is accepted in the network with a valid username, with a valid certificate, all right, can connect to any port all over the network, can even connect over wireless, can even authenticate over VPN. It doesn't matter where I'm connecting from or to which switch port I'm connecting to. The same policies are going to be automatically applied to me and installed onto that specific port. And of course, if an attacker comes in and tries to impersonate me, well, they're going to be denied access to the network. And the mention here about the agent on the slide is that, well, of course, if you plan on looking at specific details regarding the operating system or the antivirus that's installed on the host, you're probably going to have to communicate with a specific piece of software that is installed on that host, which is also one more proof that the host belongs to us as a company, that is recognized by us. If it has the valid agent that is configured on it, and that agent is reporting the status of the device to the switch, and then the switch checks it back with the AAA server, well, that's one more proof that we are dealing with a legitimate device. Finally, a couple of words here to mention about securing routing information, especially the information that comes from routing protocols. So we're talking about layer 3 here and routers, all right? And where do those routers get their routing tables from? Now, first of all, think about the fact that routers are just, well, computers that are running an operating system, and that operating system can have vulnerabilities, can have bugs that can be exploited, and any vulnerability database is at point going to list some vulnerabilities for networking devices as well. So don't think of network switches and routers being impenetrable devices. You might have everything secured in place, but due to a bug or an exploit at the operating system level, you might still be exposed, right? So another thing to keep in mind when updating your devices all over the network. Also, unauthorized information injection is another risk, which means that by default, every routing protocol out there is not going to enforce any kind of authentication requirements. So basically, whoever sends a RIP update or EIGRP update or an OSPF update is going to be accepted. Now, fortunately, these protocols do have authentication mechanisms that require the sender of the information to digitally sign the information that they're communicating. Now, this signature is going to rely on some sort of a password or a secret key, so that only legitimate devices from our network, those devices that know the secret key, can properly sign those messages. So we kind of minimize the risk of accepting information, spoofed information from an attacker. Routing update sniffing means intercepting routing updates because, as we mentioned before, these protocols basically transfer routing information from one router to another. In many cases, this information is sent in clear text, so a successful man-in-the-middle attack can easily intercept this information being sent between two routers. You might think, well, how is that sensitive information? Why is that so important? The interception of routing traffic might not be the actual purpose of the attack, but knowing a lot about the topology, the routing topology, and the devices in your network is going to help the attacker tremendously in their reconnaissance phase, understanding more about your network and what can be exploited. Finally, last risk that's worth mentioning here, or maybe not even worth mentioning actually, is source routing. Now, normally IP packets are being routed by the destination because they're supposed to reach a certain destination. So each and every router along the path is going to look at the destination IP address in order to determine where to send it next. There are certain IP options can be enabled in the IP header that can enable source routing. That is additional information attached to the IP packet that can tell a router over which hops this packet is supposed to be sent to, right? So it's instead of leaving the router decide how to send the packet already comes pre-configured. You need to send this packet to this router and this router and this router and this one up to until the final destination. Now, this is called source routing. It's not enabled by default. It hasn't been enabled by default for quite some time. It's quite unlikely that you will find source routing enabled somewhere in the network, but if you do, it's pretty obvious that along with IP address spoofing, you can even spoof this source routing information and make your packets traverse whatever path you want over the network, including a path that goes through you, the attacker, in case you want to perform some man-in-the-middle attack. Okay, so keep this in mind. It's probably not going to apply to you any real-life scenario that you might face in the near future, but keep this in mind for the exam. All right, so thanks for watching. I hope I managed to present this information in an easy to understand manner, because what's behind it, it's huge. I mean, we're probably going to create a networking training at some point, CCNA, CCNP, CCIE level, perhaps even. That's when we'll cover this in more detail, but fortunately for the Security Plus exam, you don't really need to know all the nitty-gritty details of what's happening behind the scenes. I really hope I managed to present this in an easy to understand manner. If I did, like and subscribe, support the channel if you wish, and if you can, and see you on the next video. Bye bye.